Good morning, Year 11, and welcome to another science lesson. Today we're going to be looking at calculating the efficiency of a motor. But first we need to do the do now. So if you haven't completed it already, please pause the video, go back, do it, and then we'll go through the answers. Okay, so the first one, what is kinetic energy? The equation for kinetic energy. Hopefully we're familiar with this by now. It's a half mv squared, 0.5 mv squared. Next, what is the equation for the change in thermal energy? Hint, it has specific heat capacity in there. It's going to be a delta E, because it's a change in thermal or internal energy, equals mass times specific heat capacity times the change in temperature. What is the equation for efficiency in terms of power? So your efficiency is useful power out over total power in. The equation for electrical energy transferred is E equals current times voltage times the time in seconds. So what is the electrical energy transferred by a motor that has a potential difference of 4 volts, current of 2 amps, and it runs for 10 seconds? So we'll just use that equation again. The current was 2 times 4 volts times 10 seconds gives us, I think I know the answer, but I'll use the calculator, 80 joules. And we'll be using this equation for a lot of today's lesson, so make sure you're familiar with it. Okay, so a lot of the stuff we've been doing has kind of led up to this. We want to look at a motor, so a motor that looks like this, which is connected to a power supply or a battery. That motor starts to spin round. It's converting electrical energy into kinetic energy, and as it spins round, this bit of string that's attached to the end gets wrapped around it more and more and more, and as it gets wrapped around, it gets lifted up. So we're increasing the gravitational potential energy of this mass, and we're getting the energy from the electrical energy here. Well, the energy in is electrical, so we'll be using the equation electrical energy equals current times potential difference times time. The useful energy out, so we're trying to lift it, we're gaining potential, so we'll use the equation EP equals mg delta h times the change in height. Oops, I'm really not in a steady place. Let's put it here. Let's have a quick edit of that, sorry. So I wanted gravitational potential energy up here. So we're converting electrical energy into gravitational potential energy, but we're not going to convert all of this. This motor isn't going to be 100% perfect. It's going to waste some energy. The efficiency is going to be the gravitational potential energy, that's the useful energy out, divided by the electrical energy. So our efficiency is going to be our gain in gravitational potential. That's going to be divided by the electrical, so what we put in. So let's have a look at the numbers we've got here. So we have an electrical motor is lifting a load of mass 250 grams. So I've got a problem straight away. I've got grams rather than kilograms. So if I'm going from grams to kilograms, I need to divide that by 1000. If I'm going the other way around, I'll multiply by 1000. So my 250 grams is actually 250 divided by 1000, 0.25 kilograms. We have a current of 2 amps supplied, we have a potential difference, and we have a time taken. So let's do this first box first. So our current was 2 amps. And we multiply that by the potential difference, which is 1.96. And then we'll multiply that by 5 to give us 5 seconds. And I've got 2 times 1.96 times 5. That gives me a 19.6. So 19.6 joules. So again, this is my energy in, this is the total energy in, that's going to go on the bottom of my equation. Next I need to know what the useful energy out is. So I've got the mass here, we've just converted it to 0.25. We're going to multiply that by G, which is the gravitational field strength. So hopefully remember that if we're on Earth, gravitational field strength is 9.8 newtons per kilogram. So times 9.8, and we've moved up a height of 2 meters. So 0.25 times 9.8 times 2, that gives me 4.9. And again, it's going to be joules. Remember, it's a capital J, not a lowercase j. If I use the lowercase j, I would not get the mark. So, and finally, I need to substitute these two things in. So the useful energy that I gained, that was my 4.9. Let's divide that by 19.6. Pop that into a calculator. That gives me 0.25. So remember that when we're doing an efficiency, there is no unit. So I've got joules on the top, I've got joules on the bottom, so the units actually cancel out, so I don't have any units. If I wanted to give it as a percentage, I'd have to multiply this number by 100 to give 25%, but AQA prefer you to leave it as this, to leave it as a decimal. Okay, so a lot of the questions today are kind of going to be looking back at what we've done previously. So this first question, you're just going to do a straightforward efficiency calculation, and it's in terms of energy. So it's going to be little number divided by big number. That's it. When we move on to this one, you're going to be using the equation energy equals power times time, just to show you the relationship between the two things. This one, we're going to be using potential energy is mass times gravity times change in height. So we're lifting this chap up, and then finally we're going to use all of that to calculate the potential difference, to calculate first the energy supplied by the motor, then the gravitational potential difference, and then the efficiency. So to do the electrical energy, you're going to use the equation IVT. To do potential energy, it's mass times gravity times change in height. And then the efficiency will be the potential energy divided by the electrical energy. And there we go. So use the direct instruction to help you with this one. And lastly, it's an interpretation of the pattern here. So read through the instructions here, the question here, and then use this graph to help you answer it. Okay, thank you very much.